Great. Yeah, thank you for giving me the opportunity to talk today. As Mikhail said, this is I thought for this workshop, the slightly older work that I did as part of my PhD is a little bit more relevant for this crowd. I'm currently working with Hao and John here at UCLA, doing slightly deeper kind of dynamo stimulations for Jupiter, Saturn, also ice giants. But yeah, for the sake of this workshop, I'm kind of going back to this slightly older stuff that I did during my PhD and slightly afterwards at the MPS. So working with Uli Christensen as my advisor, with Johannes Wicht, Wieland Dietrich, and then Vincent Böning was actually, so the abstract I handed in was on driving and quenching of zonal flows and gas giants, but I realized that they really needed two whole different introductions. So in the end, actually, sorry if you were looking forward to that part, but I'm only going to be talking about the quenching of zonal flows. Feel free to find me afterwards if you do want to discuss that other paper. That's the one that Vincent was a lead on. That's a 2023 paper, so I'm also happy to chat about that if anyone is interested in that work. But yeah, I'll start with my introduction then. We've had a little bit of Jupiter already this week, but I'll focus a bit more again on zonal winds. So we have these both on Jupiter and Saturn. We can see kind of manifestations of them visually on their surfaces. We get this latitudinal banding, and they're linked with these very strong east-west flows that are very steady in time. So they've been observed and tracked using cloud tracking in different observations, and they're very steady in time. They're very strong, and yeah, they have in common that they have this prograde jet near the equator. They're flanked kind of by retrograde jets next to them, and then importantly, we have this kind of alternating flow pattern that extends to the higher latitudes for both of the planets. You can also notice, there are a few things like Jupiter in particular has this kind of dip in the equatorial jet, and there's some interesting stuff going on here. But to summarize, or to look at this more quantitatively next to each other, we have the surface Rossby number, just so we get a feel for how strong these are with respect to the rotation rate of the two planets. But you can see actually if you factor in omega and planetary radius, they end up on quite similar axes. So on the right-hand side, I have actual meters per second. So we have a roughly threefold amplitude for Saturn. It's also a much wider central jet here, and then these alternating jets are also a bit wider. For Jupiter, we're at more like 10% of rotation here at the surface. So to summarize some of these key differences and similarities, we have a slightly different amplitude jet at the equator, stronger for Saturn, also wider. Both have these flanking retrograde jets, and what I want to emphasize is, they have jets that reach higher latitudes. In the case of Saturn, really up to the poles, basically. And they also have a significant amplitude, weaker than the equatorial jets, but they're definitely also very steady in time, and they're consistently being observed.
So, question?
Yes.
What are the north-south velocities relative to the equatorial velocities?
So, as in any axis-symmetric ones, they kind of have been inferred-ish using some Juno measurements, but there you have a degeneracy between inferring meridional flow, and you have to kind of factor in temperature and things like that as well. So we don't have actually a good constraint. We even talked to the ones who published the paper and asked would they give me numbers that they didn't publish, but it's very hand-wavy. They don't have something exact, but they tend to be very weak. But they kind of have a suggestion that you could have some kind of overturning cell structure that's a little bit analogous to the kind of feral cells you have on Earth that are kind of sitting between these jets. So that's possible. Convective amplitudes have also been measured. So that's work where they did really more intricate cloud tracking, where they tracked kind of correlations and flows. So there you have both the kind of non-axis symmetric U-phi flows as well as U-theta flows. And then so that's also tracking that's been done, but that's more of the convective kind of amplitude. But these are really the dominant speeds here and the dominant flow velocities. Yeah, feel free to jump in anytime. I know that especially all of this intro stuff and context is not the world most a lot of people thinking in this room. So, so we've looked at them at the surface. What do we know about these winds at depth? So this is actually, within the last 5 to 10 years, we've been able to actually get information about this from measurements, not just speculation, because, we've had Juno in situ that's still going around Jupiter, and we had Cassini at Saturn, and they measured these gravity moments, which Rafa also referred to earlier in the week. And it was always a debate up to this point if these winds were shallow or if they were deep. And there were two different communities, basically, until these measurements came about. Once the measurements came, it was very clear that they are actually deep winds. And how do we know that? It's because if they are deep, they start reaching into those regions that also have higher density. That means they have a significant mass flux associated with them, and they start to influence the gravity field. In particular, if you think about Jupiter, there the analysis was quite a bit easier because you have quite a bit of antisymmetry with respect to the equator. And that means, so as Rafa was saying, we get these gravity measurements and they're in J's, so they're in spherical harmonics. And we assume that anything that's due to solid body, so it's due to interior distributions of mass, just is equatorial symmetric, right? So we knew that any odd J's that are equatorially antisymmetric contributions, we knew they had to be due to the zonal flows, basically. There was nothing else dynamically that should be due to those. Yes?
My understanding with this was that sort of the depth of the winds as you go to higher latitudes, and even in the middle latitudes, is the constraint is far weaker. And that the only thing that is sort of known is that near the equator it's deep. Would you disagree?
Yes and no. I mean, in the case of Jupiter, the flows are weaker anyway a little bit once you start getting to really high latitudes. Also because these are much stronger flows, right? And because if you think in a spherical sense, if these are in a radial sense reaching further down, if they're closer to the the outside of the tangent cylinder, so a jet here, if it's going to, I'm going to expand all of this, if it's going to here, then it's already at a, it's having quite a big contribution in general to the mass. Whereas here, it's generally smaller, and you can see the jets are weaker in the first place. So it could be a bit disambiguous, but in Jupiter, the strongest jets are around these latitudes anyway. And in Saturn, the whole problem is a bit less well constrained because we're less sure about rotation rate, and it's also also more equatorial symmetric. So we haven't got the bonus of those really strong equatorially antisymmetric components that help us out, that are really easily separable. I'll continue with a brief overview of a very simplified way of how we infer those depths from measurements. So we make the assumption generally that these winds are invariant with respect to the rotation axis, because we're in 2 rapidly rotating planets, both periodicity about 10 hours. So we make that assumption generally, is the approach taken. And downward continue the surface measured flows along that z-axis. The next assumption made is that we would expect a decay in zonal flow amplitude to be radially dependent, because we think it should be due to something that's happening in the interior, so it should be due to something that is radially or depth dependent. So that is then multiplied on top, and what you do is you use a thermal wind equation to then see and invert back and see essentially what kind of decay profiles match well with the measurements. And you do this over a range of depths that you test and decay rates, essentially. And you arrive at your best fitting solutions. Oh, was there a question?
I think I asked you this before, but I guess how can you be both radially dependent and see invariant?
So we assume that this outer region is fully convective and dominated by rotation. So we assume that essentially you see that here, so this is here the outer radius. So here they're essentially one. So this is where you're structurally invariant with respect to Z, and also you have the same amplitude as at the surface. And then your decay function starts kicking in, and you're structurally still aligned with Z, but you're decreasing in amplitude in R. Does that make sense? If I show you, so if I now plot basically the two functions, so what we result at, these two 2D profiles, I plotted them on rectangular grids because you can see, especially for Jupiter, we're talking about the outer 3% here. So you can't really see much if I was going to put this on a pizza slice. So you can see this curving of the flows in this direction because we're Z invariant, the structure-wise. But then they are all being quenched at kind of this one radial level. Yeah. But yeah, so they're assumptions we put in when this data, these measurements are being analyzed. But there are slight variations with different publications, but this is the broad method. Yeah.
At 0.97, it's varying in every direction.
So if you think of like, yeah, it's a case basically of saying structure varies like this. So where your peaks and your minima and maxima are is varying in respect to Z. But then an overall amplitude function, in a way, is radially dependent. So it's two multiplied together. So it's really just multiplying this by this, essentially, is what you arrive at. So this leads us to what I want to emphasize, okay, if I was saying, okay, this is only like 3%, that makes it sound like it's really nothing, but let me emphasize that especially in this community and with this historical debate around the subject, these are really deep-reaching winds. Firstly, they're leaving an imprint on the gravity, and secondly, we're going through like 4 or 5 pressure scale heights within this depth. So this is considerable, even if it sounds like, oh, 3% isn't much. But this is actually significant, and you can see for Saturn, they're even deeper, actually.
So what's plotted? Is it like, which component of
U phi.
U phi.
Yeah. So it's really the zonal flow that I showed on the surface as a surface profile earlier, and then downward continued with that radial decay applied. So this is what we think they look like in the interior.
So I'm still confused about this penetration of coherent rotating vortices through many scale heights.
I wouldn't say vortices. It's zonal flow.
No, I know the zonal flow, but okay. Your assumption is that the deep convective columns dominated by rotation are these vertically aligned things that penetrate most of the atmosphere along the axis of rotation.
No, it's not necessarily that the same structure, like in a sense of vorticity, really reaches down all the way, but that mean zonal flow is Z invariant through the convection region. Does that make sense? So it's only in a very statistical sense that the small scale motions are, aligned and correlated in a way, and then form cylindrical structures along Z. But if you were to look at a snapshot, it's not really like, like this. Like, so you have a vortex that's really just going down all the way between. That's very much an idealized view. But for U phi, so for zonal velocity, we think that is like a mean flow that really continues downwards. If that makes sense. Yeah. Okay. Okay, so this makes us think what is happening at that depth in the interior that could be leading to this decrease in amplitude. So if we look at the two planets, and the gray shading here is electrical conductivity and Siemens per meter. What you can see is that we go from very weakly conducting, essentially we're hydrodynamic up here, where we have molecular hydrogen, so where pressure increases, density increases, we end up with metallic hydrogen, and with an extremely conducting zone down here where our dynamo action happens, etc. I've kind of made this kind of level a little bit more obvious just to kind of give a bit of a reference. It's not that something special happens at 1 Siemens per meter, but just to give a feeling of roughly where we start having to think about electromagnetic forces. And if I zoom in on this region and I put in my zonal flows, it is kind of a bit obvious, quite obvious that there is a link there for sure. And that electric conductivity must be playing a role somewhere in this quenching. But the question is, how does that actually happen, and is that the only thing that's happening here? So now if I give a little bit of background on numerical simulations, which is the way that I approach this problem, so I'll show work actually that John was involved with. These are actually quite old simulations now, they're 20 years old. But we already managed to get zonal flows.
Rough meeting.
So this is work led by Moritz Heipel, but that John was involved with. And this is a spherical shell, like you can see, and it has stress-free boundaries both on the bottom and the top. And you think, great, we're getting these multiple jets. They look, not too far from a kind of Jupiter-like jet structure as well. However, just having a stress-free boundary condition at the bottom here, that doesn't help us answer the question of what is eventually causing the winds to be truncated, right? So now we go about 10 years on, and there's other work around this as well. I just picked one publication. So that's what happened. Let's see what happens if we put in a radially varying electrical conductivity that's shown on the right here. 3 different cases where it's a normalized profile. So we're essentially conducting down here. They varied this and then to be non-conducting in the outside. And then you can see the 3 corresponding surface profiles for these cases and one example of a 2D profile as a slice in the sphere. And what you can see is that we've basically eradicated any of these higher latitude zonal flows. We only have one, essentially, we have our prograde equatorial flow. We have one, these flanking retrograde flows, but we don't have any alternating pattern. So that's neither Jupiter nor Saturn-like in that sense. But this is clearly something that's happening in the interior, so we need to be able to figure out, what's missing, what's the missing ingredient here.
So is it basically just magnetic damping?
Exactly. Well, in a way, it's basically if we were to force the zonal flows from the top here, the Maxwell stresses you would get at the bottom when they reach that electric conducting zone are so strong, and because this all wants to be invariant with respect to Z, then breaking that is so strong at the bottom essentially means that those winds don't start to form above. If that makes sense. Yeah. And what I want to add here, this is something I've discussed with John actually, it's a symptom of our simulation, is we actually get something very similar happening if we put in a rigid boundary at the bottom. So say in a case like this, if the bottom boundary is rigid there, we actually get something that's a bit similar to the other case. So we don't get alternating flow here. We pretty much only get zonal flow that lives slightly on the tangent cylinder / outside the tangent cylinder. Okay, so in these numerical simulations, in a way, it can also serve as a proxy for an electric conducting region below. So that's just something to bear in mind later when I introduce some of the work we did. I did debate with John because, in experiments, you do get zonal flow developing with an obviously rigid boundary. So it could be a symptom of our too large Ekman numbers here. However, I don't think it's the case for this because that's not a viscous effect, right? So I think that this is something that is directly transferable to planets. But with the case of having rigid boundary conditions at the bottom and seeing the similar thing, that could be a numerical simulation thing. We kind of debated on this, but yeah. But okay, so there's clearly something missing here because if we're double stress free, then great, we get these high latitude jets. but we're not answering the question about truncation. If we include our connectivity profiles, we're not getting those multiple jets, so that's also not really answering a question about truncation. So there's something missing, and that's something that Uli Christensen's proposed in 2020 in a paper, was the presence of a stably stratified layer in this region where the quenching is taking place. So let me now introduce the models that I carried out for this work. So firstly, we'll start with some spherical shell models. Just as a brief, we've seen these equations several times this week, so I won't put them up again here now. I use magic, and I can do this using the anelastic or Boussinesq approximation. I've done some cases for both. I did both a hydro study, so that's the first 3 equations being solved, and also an MHD study where we include that last one. The setup for the hydrodynamic model looked something like this. So we had an outer, roughly the 2/3 were convecting. Then the lower third is stably stratified. You can see that I'm not trying to do exactly Jupiter or Saturn directly here, because this physics has actually never really been studied before. So we want to just fundamentally understand what happens when we have a convective region overlying a stably stratified one. Then as a proxy for electromagnetic forces at depth in this study, I put in this rigid lower boundary condition. And just to simplify the problem as much as we could. And what I varied was the degree of stability of that stable layer, so of this hatched region, which we quantify by the ratio of the Brun-Weissaler frequency to the rotation rate. In my other study, then MHD study is very similar geometry, but instead we now have an exponentially increasing electric conductivity. That's this gray shading here. That's something that we varied. And we also imposed an axial dipole at the lower boundary as a proxy for dynamo action happening below. And the things that we could then vary instead was the profile, so both the slope and the amplitude of our electric conductivity, and then also the amplitude of the axial dipole at the bottom. And this one we summarized in terms of an Elsasser number, which is both, you can see as a kind of radially varying profile, and also evaluate locally. I'll be showing plots using both later on, but which basically summarize these 2 things we are varying by the b squared and sigma. Okay. So let's get to some results. So the general picture of what we're expecting in these simulations, as I said, this is the naive view. We don't actually have these cylinders extending all the way down, but we generally expect, yes?
Sorry, maybe before you go into the results, can you just have a question about the setup? How do you maintain the stable stratification?
It's an imposed entropy gradient. So in the stable layer, that's positive to a specific value that is then corresponding to the n over omega that we want, so ds by dr. And then in our convective region, it's set to -1 to drive the convection.
Okay, but isn't the convection then going to eat into the stable layer?
It's a fixed profile, so that can't shift in the simulation.
So the
It's
radial profile, the entropy is fixed in time?
The entropy gradient, a background entropy gradient.
That's fixed?
Yes.
Okay.
Are you Boussinesq here?
So in this first study, I was all anelastic. In this, I did some of both. So the big study was Boussinesq, but I did additional anelastic to make sure we get the same thing.
So you don't get any, so the convection itself doesn't change the average entropy?
No. So it's not let to freely evolve. You can get penetrative convection, just as in, or you can get structures that impinge, depending on n over omega, but ultimately the profile is fixed for the whole simulation.
So every time step you like zero out the...
Well, it's like a background profile. So we have a fluctuating entropy around it, and sorry.
Yeah, can I add something here? So in the simulations, the convection does develop an average background entropy perturbation as well, but that's very small compared to the background stabilization they put in, because they put a huge background stabilization, say -100, and you
Okay.
basically get it like 1.
Yeah.
So,
Okay, great, thanks. That makes sense.
Okay, so yeah, what we kind of expect just from theory is that, yeah, the small scale flows start to correlate, and then we end up with this a kind of mean zonal flow. So if we look at a kind of polar view of the simulation, that is actually what we observe. So we can see around the poles we're getting this kind of prograde jet that we want, and then we get this alternating profile that extends to the poles. If we now kind of dive further into the simulation, so bearing in mind, so something dynamically that could be interesting is the tangent cylinder of, firstly, it's often where that retrograde jet sits, and it's kind of a separating our dynamics, right, in these simulations. So if we look at the simulation and we start cutting downwards with depth, we can see, we're transitioning from our kind of convective region here to these much smoother flows here. And we can see that actually the dynamics tangent cylinder in these cases is actually controlled not by the inner lower boundary of our shell, it's controlled by the boundary to the stably stratified layer. So that's something that's interesting, maybe not trivial, I would say. If I now look at what these kind of can look like in a time average state, so this is an example of some of the profiles we can get. As I said, you can see this alignment of the tangent cylinder with this boundary. So bearing in mind kind of the title of the workshop, I thought actually this is a quite interesting type of boundary that is happening in the system here, because we clearly do have flow that kind of crosses over it, but it's the one that is controlling the dynamics of this outer zone. If I make a comparison, like I said, I was varying, so this is this example with rigid lower boundary condition without a stably stratified layer. I go across and I introduce my stable layer and increase the degree of stability, quantified by n over omega. I see that I get more and more zonal flow developing at also the higher latitudes. So effectively, the stably stratified layer is decoupling my convective region above with that harsh mechanical boundary condition, which is what we want, right? Yes.
How long do you run these things?
So,
for example, do you run it long enough for an Eddington sweep time in your stable layer to actually set up meridional circulations?
So we definitely, we'll have a look at meridional circulation and stuff later as well, but it's the first one for, like, let's say 10 viscous diffusion times when you start really just with your very first case. Obviously you get to that slowly in a sense, but then each individual one for like at least 1 viscous diffusion time, if not 2. These are this study was Ekman number 10 to the minus 5. So yeah, it does start to get a bit pricey otherwise. Mm-hmm.
So these are in thermal equilibrium, I assume?
Mm-hmm.
So what's carrying the flux? So you have a convective flux in the convective region, and what's carrying the flux in the stably stratified?
The SDT, the SDT.
Well, there's no flux, then it's not in thermal equilibrium.
No, it's divergence free. It's the background has 0 heating. It's
Conduction.
Conduction.
Mm.
Okay.
There's nothing, dude.
Yeah.
Did you, my favorite question, did you look at the kinetic energy spectrum?
Yeah. Yeah.
Show it. What is it?
Oh, I don't have it with me. I mean, it's a strong function of radius, right? So it only makes sense to also look at it as a
Did you look
2D
at
spectrum.
the flow? This is what I'm asking.
In these cases, I think I gave them to Vincent, who wrote the other paper that talked more about this stuff. I think I did give him some of my cases with a stable layer to look at and do more fittings with. I can't remember if he found anything. I think if you do look at the convective region, you get something very similar to if there's no underlying stable layer, if you're looking at the convective region then. But I can't remember the specific, slips. Yeah.
The conduction, is it entropy diffusion or temperature diffusion?
Yeah.
Okay, so you do have a mean entropy gradient in the fluctuations in the stable layer in order to gain flux equilibrium.
Yeah.
Okay.
It's a hyperbolic.
Yeah. So this background that I set is essentially so background use a tilde ds by dr. So I essentially have some value that's my stable layer that I set. I have a hyperbolic tangent, and I go to like -1 here to drive the convection.
But then you have fluctuations in the spherical average in the stable layer so that you can transport the heat from the convective layer, right? You're in thermal equilibrium. You said that there's a convective flux.
Small compared to.
Yeah.
Okay, and that's small.
Yeah.
So you're solving for the fluctuations around.
So it's the same approach that magic or similar codes take towards other background profiles, in the sense that you assume the fluctuations are much smaller.
But if the diffusivity is very small, then you need a big gradient to transport the convective flux. But in practice, it seems like it still is smaller than this entry gradient that you have here.
Yeah, I think it's still. I don't know if Mike had, yeah, he had a question.
So I'm just trying to understand the motivation for this a little bit. So you have no slip boundaries on the interior, right?
As a proxy to keep it as simple as possible, because we said, okay, let's start with this hydro case and just look at the effect of M over omega changing.
Yep.
So we use that boundary condition as a proxy for electromagnetic forces at depth, because in numerical simulations, we see this as a kind of analog that it has a very similar effect to as if electric conductivity was increasing.
But I mean, the more stratified you make that layer, the better you're going to hide that no slip boundary.
By stratified, you mean the extent or N over omega?
N over omega.
Exactly. So that's exactly what we see.
Right.
So essentially, it's decoupling, right, the convective region from the harsh boundary condition, which is kind of what we're interested in when we get to the MHD study is what we're interested in doing, right? We want to, in this case, we're decoupling from viscous effects from the boundary condition. But in an MHD case, we want to see, will we decouple from too harsh electromagnetic forces? Okay. Yes?
So do you start to converge towards the stress-free solution depending on how your stable stratified layer is?
It is very similar. I didn't include the plot here, but in the paper, I have one where it's the aspect ratio basically of the convective region. And the zonal flows do look very similar to the one. So this is the most extreme case here, actually, where it's about 10, the ratio. And they do start to look, it's not exactly identical, but yeah, there is no, you can't, if you just looked at the surface flow, you wouldn't really be able to tell the difference. Yeah. Yes?
Just really briefly on this, if most of the gravity measurement is kind of actually coming from lower latitudes, then I guess the question I have is, which again, maybe that's not true, but if that were the case, then these simulations actually that different in terms of the observation you'd make of the gravity field? Because they're, as you've said, like the sort of more equatorial region, it actually kind of looks the same in all of them. So you're sort of talking about instead of these changes in the mid-latitudes, but does that have much of an observable signature?
Well, in the sense of we see them on the surface, right? We clearly see a profile that varies in amplitude.
But right at the surface, you could just have something like baroclinic instability.
Sure, there is a big debate, and that's something that Howell looked at actually. What if you don't input actually the measured surface flows to when you're doing this gravity analysis, and instead you let it be some polynomial? And what you get is something that is very close to the measured flows. Of course, the strong flows leave the strongest signatures. So that's the stuff that is more directly reproducible that way. But yeah, we'll see later on if this mechanism should have any change with respect to latitude or not. So I might be able to address some of that later as well. It's a good job I didn't try and cover both the generation and quenching of flows in one talk. But this is great, so keep asking if we'll miss the end of the talk, otherwise it doesn't matter. So another thing, to be able to quantify this, what I looked at is then a kind of penetration depth that I defined like this in this case, that's evaluated locally on the boundary here. between the stratified layer and the convective region. And the other key thing that we knew to kind of expect from penetrative convection work was that this is probably going to be a length scale dependent thing. So that's why, we did a comparison when we include it, when we don't include it, and in the end it fits much better if I use a length scale, which I define like this. So that's the arc length, essentially, of when the jet reaches that boundary, which I call A. And then if I plot this for all of the jets in my simulations as a function of n over omega, so here I have penetration depth divided by A, just so we're non-dimensional, as a function of n over omega, so stability. And you can see that the penetration depth clearly decreases as you increase your degree of stability. So the higher n over omega is, the less these winds can penetrate into the layer. And also, we see this dependence on A, so wider jets also penetrate further in, whereas narrow jets are quenched more efficiently. Okay, so they are the main results from the hydrodynamic study. If I now jump over to the MHD study I did, so I'll quickly remind you, I had this electric conductivity that was increasing with depth, and I had an imposed magnetic field at the bottom. I can compare two extreme cases here where I kind of just as a reference have indicated Alsacer number on the boundary, just so we get a feel for these two extreme cases. So the left one has a much smaller Alsacer number on the boundary, so that's due to a low electric conductivity, and I've imposed a less strong magnetic field. On the right-hand side, it's a stronger magnetic field imposed, and also electric conductivity is also greater already at the boundary. And we can see the immediate effect on the winds. So basically, the one on the left, the stably stratified layer, is protecting that convective region again, just like we saw with the other cases, the hydro cases I showed. And we get wind formation happening at the mid to high latitudes. Whereas in this case, electromagnetic effects are already too great at the boundary here. So that convective region is noticing that we have Lorentz forces and that there is something that wants to stop this shear. For these, it's 3 times 10 to the minus 5. If I scale that to the convective region, we're at still slightly below 10 to the minus 4, I think. So that's always the case when you start dividing up your shell. Of course, effectively, you're a little bit higher, but
sorry if you said it already, but what's the shape of the magnetic field you're imposing?
So this is just a dipole that is imposed. So the strongest, when I include amplitude, it's the value at the poles, so the strongest, and that's what I vary, and then it's, basically a dipole at the lower boundary. And when I evaluate this Alsacer number, I also take basically this imposed one. I only pose it at the bottom boundary, but it is the strongest part of the field, so as a kind of, to be able to do it analytically, I just take the amplitude of that dipole through the shell. What I'm mainly interested in here, we know, I've said, okay, we can do prograde equatorial jets, they're kind of fine. We sorted those out. The ones we're interested in are the ones up here, so inside the tangent cylinder. And if I try and look at that quantitatively, I can integrate these and get an RMS amplitude of velocity inside the tangent cylinder for all of my cases. And if I plot that as a function, this time of this locally evaluated Alsacer number, I can see this clear drop with increasing Alsacer. So the case here is our extreme case on this end. This is the one on the left here. So we can see that once our electromagnetic effects start to encroach on that convective region, then we really inhibit the formation of those zonal jets. Whereas here we can see we're starting to plateau off, and the further away from that boundary any kind of magnetic field and electric conductivity is, the less the convective region knows about it. Okay. Now, if I think again about the penetration depth of the winds, so I'll just illustrate this first with two cases on the left-hand side. So this is just to get you more of a feel of the variation of the Alsacer number with respect to radius. This is two extreme cases again, so solid and dashed. And if I then look at the amplitude, this is amplitude that is averaged over each jet maximum amplitude and normalized at the top. I can see that, so for the dashed line, which has the much bigger Alsace number, the quenching of the jet is much more efficient. It really drops straight after the boundary. Whereas the one which has a much lower Alsace number, it takes almost to the bottom of the shell to really drop off to negligible values. And I can do that again for all of my simulations, and I can see this clear trend line. So what is now physically causing the truncation of these winds? So to do that, first we're going to look at the thermal wind equation. So to kind of, I won't go through and convince you or look at all these terms themselves. I did, but all of the extra terms here actually turn out to be very negligible. And you're left with the classic thermal wind balance, which is our vertical variation of zonal flow and the latitudinal temperature in the case of anelastic entropy variation on the right-hand side. So let's see how well this holds for one example case. On the left, we have zonal velocity, just to give an idea of where those jets are. And on the right, we have the two components of the balance, and we can see it fits basically perfectly. You can see I've oversaturated a little bit in the stable layer. So actually, in this outer region, it is very small. Like this kind of catches the eye. We have a little bit of variation with respect to Z in the convective region, but very, very little. And you can see, obviously, where those zonal flows are then being quenched, we have strong contributions. So we have strong variations of entropy with respect to latitude. And the question is, what is setting up that meridional circulation? To do this, it's a bunch of equations. You don't have to care about them if you don't want to. Basically, this is the axisymmetric force balance in the azimuthal direction. I've highlighted the ones that we're going to care about. So that's the Coriolis force, which, in the phi direction, or also time average, I should say, or steady state. Coriolis force in this azimuth direction is basically meridional flow, where S is the cylindrical radius. Then we have Reynolds stresses, or more precisely in the force balance, it's divergence of Reynolds stresses. And thirdly, what I've called FMA, so that's axisymmetric magnetic effects, or Maxwell stresses. And the reason why we care about these large-scale Maxwell stresses in this case is because all of our Lorentz forces are acting in a stably stratified layer where we don't really have small-scale flows. So that's why these small-scale correlations of magnetic field are negligible, right? So if we're thinking more about a fully convecting case, then these will be really important. But because all of our MHD is happening where there isn't convection, it turns out that actually only this term is doing the heavy lifting here. Yes?
What's your lower thermal boundary condition? The fixed entropy or a fixed gradient or?
Fixed entropy flux, fixed entropy gradient. Okay, so let's have a look what these look like in spatial space. So for one example simulation, I've not included the whole convective region here. I've only included what's close to the boundary. So if we first look at what the balance is near the boundary, is that it's clearly between Coriolis forces and Reynolds stress divergence. This is to be expected because we have a strong component from the Reynolds stress divergence here because, because if you think about the term, it has these small-scale flows in it, and especially the radial ones, they're being quenched, right, as soon as they hit the stably stratified layer. So we would expect a strong divergence of zonal stresses here. And the thing that balances that out is a meridional flow, so Coriolis force. So we have flow towards the poles. Lorentz forces don't play a role yet because we're not really electrically conducting yet in this case. If we look deeper down, then the balance shifts. Reynolds stresses are doing nothing. There's no small-scale flow, and our flow is not very well correlated anymore. And instead, it's this meridional flow, or Coriolis force, balanced by these large-scale Maxwell stresses. If we look at the case where this braking was more effective, you can see how this whole mechanism is basically shifted upwards. So I've kind of sketched in the zonal flows just in gray here, so you can see the outlines. So this is a case where zonal flow doesn't penetrate very far into the layer. I'm going to, okay, we won't get to other stuff, but okay. And you can see that the whole mechanism is shifted upwards, as have our meridional circulation cells. So that's why our braking was much more efficient in this case as well. I probably won't get to, okay, I'll summarize quickly the work I did with Uli. So we won't go through, basically Uli did an Uli thing and basic non-dimensionalized, scaled the equations in a very clever way. So you end up with this very simplified version of the equations. He did this in a box basically here. So instead we have everything zonal in the y direction. We can vary the location of this box, so these two angles. So that's then the angle with respect to rotation rate, also magnetic field, for which we assume the dominant dipole field. And yeah, I'll cover whatever else I need to cover when I try and explain results. And basically what you can see is in these equations, so k is a wave number here, so everything was expanded in terms of sines and cosines. And so the only actual variable that is left in these equations that is a control variable is what we've called the Mach number, which is expressed by this. And we call it the Mach number because you'll see magnetic effects in there. If we separate that out, we get an Alsacer. See Archimedean effects in there, so that's our n over omega. And we see Coriolis in terms of this kind of thermal Ekman number, if we kind of split this whole thing apart. Yes?
Or what's the Mach number in this model?
Oh, I have no idea. We don't really think about that.
You mean the actual Mach number?
Yeah, so I'll quickly try and summarize the results. I hope there's slightly enough context in there for them to make sense. So basically, this Mach number is something we can evaluate, right? If we plug in kind of interior profiles, say from French et al., Nadine's, etc. So we can basically have them pick this as our x-axis or Mach number as our x-axis. And this x-axis is the depth of the stable layer boundary. And so we can say that, okay, depending on wherever we put this boundary, we can evaluate the penetration depth of zonal flows, the power, the driving power of the jets, and also the associated magnetic Reynolds number. If I go through these one by one, basically you can see that this jet penetration decreases. So this is where it's decreased by tenfold. The deeper that boundary lies, we can see that if we think about the driving power, that this increases as a function of depth. So this makes sense, right? It's like what I was showing earlier in my models where I could evolve freely. I was getting less zonal flows if my electromagnetic effects were already great at the boundary, right? Because, I would need more power to drive them otherwise. So that's, it all fits in very nicely with what we saw in the 3D models. We can also use this to place constraints on where we think that layer might be based on the dissipation or the kind of the dissipative heating from Jupiter, for example. So that's these two lines. We could use an indicator here that could place a kind of bound on where that stably stratified layer should be. And finally, we can also say that, okay, the magnetic Reynolds numbers we get shouldn't be too great because otherwise these flows are going to start perturbing our poloidal magnetic field too much, which we don't see on the surface. So we can also place a bound on, on this axis, which is very similar actually to the one that we placed based on the power. And also say that this layer and the jet quenching shouldn't be deeper than about 2,600 kilometers. So I'll miss this. This is just showing that it's not very, the penetration depth isn't very dependent on co-latitude. That's one I didn't show. But it is the power is a bit dependent on latitude. You can see that higher latitude jets require more driving power than lower latitude jets. And don't need to summarize this one, but just to give you a final overall picture. So we think that to have these kind of zonal flows that extend to high latitudes and to be able to have them being quenched at the depths that we infer from gravity measurements, that we must have a stably stratified layer being present here. This is exaggerated. It wouldn't really be this deep, at least on Jupiter, because otherwise you start smoothing out your magnetic field. On Saturn, that's less of a constraint. But on Jupiter, it's likely to be a very thin layer. And with that, thank you. Sorry, the rest was rushed, but the questions are good.